So galvanic cells use spontaneous redox reactions to generate electricity. So the components of a galvanic cell are that we have what we call a half cell, which is a container that will have an electrode of a metal, and in the solution will be that same metal as in ionic form as a dissolved salt in solution. So we have two electrodes, a zinc and a copper, so they do need to be of two different metals. We have a salt bridge that then connects those two half cells, and that salt bridge is packed with a soluble salt, and we have a connecting wire in between the electrodes that allows the electrons to flow. Normally we would put a device that we actually want to use the electricity in between so that the electricity is then generated. So we can also use a multimeter or a voltmeter to measure the voltage that's actually generated. So in our galvanic cell, we've got to work out which one is the actual anode that is oxidized and which one is the cathode that is reduced. So we can do that in a couple of different ways. We can actually look at our reactivity series. So this is our reactivity series out of our data booklet. So we're looking for the two actual metals of our electrode. So we're looking at zinc and we're looking at copper. So copper is less reactive than zinc. So it really wants to stay as copper. So it's very unlikely that it's going to be oxidized to form the copper ions. So zinc is more reactive. So it is actually able to be oxidized. So it will form the zinc 2+ ions through oxidation. So the more reactive is oxidized. More reactive is oxidized. And if it's oxidized, that means it is the anode. So our cathode in this case will be the copper. So if I go back to my diagram, I can then label these as this will be the cathode. So my copper is going to become the cathode, and my zinc is going to become the anode. So we've now got these. The electrons always flow from the anode to the cathode. So they always flow anode to cathode. My anode is in a galvanic cell is negatively charged. And I remember that with N for negative. So it is negatively charged. And I remember that the T looks like a plus. So the cathode is positively charged. So our anode is always negative, our cathode is always positive in a galvanic cell. Anode is also our oxidation side, and cathode is always our reduction side. So a mnemonic to help you remember that is an ox and red cat. So anode, oxidation, reduction, cathode. So what's actually going to happen here is that because the zinc is being oxidized, the zinc will become zinc 2+. And this will get degraded. And at my cathode, the copper ions are being reduced to become more copper. So if we didn't have a salt bridge here, then what's going to happen is I'll get a buildup of positive charge occurring here because I'm getting more and more of these zinc 2+ forming. And over here, I'll get a reduction of positive charge. So I'll get a buildup of negative charge. So what actually happens as the salt bridge, and the reason this is important, is that my negatively charged ions, my anions, they go towards the anode to balance out the buildup of positive charge. And my positive ions, the cations, move towards the cathode to balance out the buildup of negative charge. So a mnemonic to help you remember that is anions move to anode, so they have the same beginning, and cations move towards the cathode. In terms of this is where we're talking about the salt bridge. So my electrons here, I've generated 2 electrons, they've moved across, and those 2 electrons are then used by the copper 2+, which is migrated here, to actually form the copper. This is our labelled diagram. Another way of actually looking at then how much electricity is actually being used is to use our standard electrode potentials. Now these are for 1 molar solution, so I would need to make sure that this actually states that it's a 1 molar of each of these solutions, and would hopefully also tell us that it's at 25 degrees or 288 Kelvin, and that it's at standard pressure. So if I'm looking at this, I want to then look at, well, what is my actual maximum voltage that I would get at the beginning in terms of theoretical. So I have my zinc 2+, which can produce negative, its electrode potential, reduction potential is negative 0.76, and I have my copper 2+ going to my copper solid, which is my 0.34. So again, I could use this to actually work out which one becomes my cathode. So my more positive one becomes my cathode, and my anode is the less positive one. So in this case, it's actually negative, but if we think of more positive, less positive. So let's look at then what it would actually be. So I have my 2 half reactions of my reduction, giving me my copper solid, and it's got an electrode potential of positive 0.34. And if I write it as the reduction, which isn't actually what's going to occur, it will be going to the zinc, and its electrode potential is negative 0.76. So I'm just writing this at the moment to show you one way of calculating the electrode potential of the cell. So the way I do that is to do my electrode potential of my cathode minus the electrode potential of the anode. So then I have my positive 0.34 minus negative 0.76. So that would then become the same as doing a plus 0.76 because the negative and the negative cancel each other out. So 6 and 4 is 10, and 8 and 3 is 11. So it's going to be a positive 1.10 volts. It's a theoretical electrode potential difference that can actually be generated with this cell. This is one way of looking at it. The other way is that if I then actually write the oxidation, so I'll leave my reduction as the way it should be. If I write my oxidation the way it actually is running, because I'm going to reverse the reaction, I also need to reverse the charge of the electrode potential. So if I write it as the zinc solid is actually being oxidized to the zinc ion, then I need to reverse the sign of my electrode potential. So if you write this like this, it's simply a case of then actually adding up the 2, which gives me my positive 1.10 volts. And this means because it is actually positive, that it is a spontaneous reaction. If I was trying to have the zinc being reduced, this would actually generate a negative because this would be the cathode and this would be the anode, so it would be a negative value, which means that it's non-spontaneous, so it wouldn't actually occur that way.